Okay, on the video I recorded a minute ago, I introduced this idea of fracture flow and the incredible importance that fractures play in controlling how fast water moves through the ground. That, of course, has huge implications for the movement of not only water but of pollutants, which we'll come to next week. And again, I was sort of showing this thing here, right? So this says that for a given thickness of an unfractured aquifer, with a given hydraulic conductivity, you get a corresponding amount of flow that would be equal to water that could be pumped along a fracture of a given size. So we said, for example, that if you had a 1 millimeter fracture with, if you had a 1 meter, if you had a 1 meter thick chunk of rock with a hydraulic conductivity of 10 to the minus 3 meters per second, which is 10 to the minus 1 centimeters per second, that same amount of water could be pumped along a single fracture with an opening of 1 millimeter. Okay. So what are the consequences of that when we are analyzing or constructing or testing for hydraulic conductivity? And this graph, I think, does a pretty nice job of illustrating this. So we talked about 3 different ways that hydraulic conductivity can be measured. On a very, very small scale, you can stick a boring device in the ground and collect something about the size of a big jar of peanut butter and take it back to the lab and use a constant head permeameter to calculate the hydraulic conductivity. But that only allows you to determine the hydraulic conductivity for that one tiny little chunk of sample that you collected. You can alternatively do an infiltration test, a perk test, a slug test, that will allow you to assess the hydraulic conductivity of something considerably larger, but still in the size of a room maybe. Oftentimes you want to do it multiple times to get a sense for what the average hydraulic conductivity is like in your yard before you put in a septic tank. And then if you really want to get a sense for the hydraulic conductivity over a broad area, many, many hundreds of meters, we would use a pumping test where you would examine the shape of the of the cone of depression after pumping for a while. And you can do that by using monitoring wells. So this is something we've talked about before. Well, this gives you a sense for how difficult dealing with small-scale fractures can be when you're trying to assess hydraulic conductivity. This is sort of an extreme example. Each one of these little horizontal layers here is a bedding plane of lava flows. Now, we're not going to have lava flows to deal with in Iowa, but in the Pacific Northwest and in the West Coast and even parts of the East Coast, you might see it. Certainly in Hawaii and other parts of the world. So you have a lava flow and then another lava flow on top of it and another lava flow on top of it. And each one of these little squiggly vertical lines represents a cooling fracture. So when hot materials cool, they contract, and sometimes you get these little cracks that form. And those cracks obviously are fractures that allow water to flow very, very easily along them. So what this is supposed to show, right, is what would happen if you went in and you sampled that very smallest little circle right there using one of these boring devices, and you took it back to the lab and you measured the hydraulic conductivity. And so up here we have, this says value of parameter measured. We can think of it in terms of hydraulic conductivity. And this is the size of the area that we're testing, right? And the idea here is that as you take slightly larger and slightly larger samples, they only show 3 different ellipses here, but here probably there would be dozens. The idea is that as you take slightly larger and larger samples, what you're getting at is a very, very different kind of hydraulic conductivity for the entire aquifer. When you stick your little coring device into the rocks here, you may or may not hit a fracture. If you don't hit a fracture, you would get a very low hydraulic conductivity when you take that back to the lab and analyze it. If you do hit a fracture, you're going to get a very high hydraulic conductivity. And so depending randomly on where you take that sample, there's going to be a lot of noise in the system. As you take samples from larger and larger test volumes, as long as you're staying within this individual lava flow, you are eventually going to sort of they're going to coalesce on some sort of value corresponding to this relatively flat line here. But as the volume gets even bigger, now we cross from just having these vertical cooling fractures to now having these horizontal bedding planes. And as you recall from whenever it was, a week or so ago, bedding planes are a really nice zone of weakness that water likes to flow along. So once your test volume is big enough that it starts overlapping multiple bedding planes, the hydraulic conductivity is going to shoot up again and plateau at a new level. So it can be very, very tricky to assess hydraulic conductivity, and it's something that you need to do in a way that is corresponding to the question you're trying to answer. In order to assess the hydraulic conductivity of something like this in terms of its feasibility as an aquifer, you'd use a pumping test. In order to look at its ability as its potential to house a septic system, right? Clearly, a perk test would work because these fractures are of sufficiently high density. Anyway, it's something that you have to keep in mind.